Hi, we're going to get started on our very first lecture for Chem 266, and we're going to start with the focuses on quantum theory rather than starting with thermodynamics and kinetics for a couple reasons. That goes better with the order in the computational physical chemistry book that we're going to do that material. And also, quantum theory is something that you probably haven't seen, at least not in this way, actually seeing the math and solving Schrodinger's equation. So should be a little more exciting maybe of a start, at least I see it that way. When we go back to thermodynamics and kinetics, most of what we do, you will have seen in Chem 107, 108. It'll just be at a little different level using the math and deriving more of the equations that you use. So you will have seen the topics before. This should be a little bit new. So I'm going to plug in the camera, which I can't do before we get started because then it turns off the other camera. So I'm not expecting you to be able to actually read this very well, but what I'm going to try to do is do the lectures as if I'm reading the book to you. So you have your book, you can follow along. Sometimes I'll zoom in a little bit on a section if I need to show you a diagram. But in general, I'm going to try to read it and give you what I consider are the important parts of it. So here we go. So this is just the overview of the topics that we're going to cover. So we're going to talk about why quantum mechanics was developed, what was going on at the time, what experiments were being done that led us to think that we needed a new theory. So classical mechanics was used before quantum theory, but when you get to the point where you can design experiments and actually measure the properties of small particles, what you discover is that classical mechanics doesn't work. So that's what we'll go through in this very first lecture. The next is just thinking about what a solution using quantum mechanics means. So what is the dynamics of microscopic systems? And that's just looking at, from a chemist's point of view, what does an atom look like? What does a molecule look like? And how do we solve those systems using quantum mechanics? And then after we do that, we'll look at 3 different types of motion: translation, rotation, and vibration. Those are 3 different places you can put energy within an atom or a molecule. So a molecule can rotate, bonds within molecules can vibrate, the whole molecule can translate or fly through space, and also the electron's motion relative to the nucleus is considered translational motion. So we'll look at the solutions to those problems using quantum mechanics. So for the emergence of quantum theory, what you need to know is that at the time, it was about 1900. So I think it was 1905 that Einstein got the Nobel Prize for his work on the photoelectric effect, which is one of these experiments we're going to go through that led to the development of quantum theory. So experiments are being done for the first time in the early 1900s with new equipment so that it was understood that classical mechanics couldn't be used to understand atoms and molecules. Each of these always tells you what you need to be familiar with. I will make sure we don't go in an order that you're not going to be ready to learn something. So the 3 experiments we're going to talk about are, number 1, the experiments that were done to show that energy within atoms and molecules come in discrete packets. So you can't just add any amount of energy to an electron or a vibration and expect it to be absorbed. It's always discrete, so certain size packets of energy. The second experiment is the photoelectric effect, which led Einstein to conclude, he didn't do the experiments, of course, but analyzing those experiments, he concluded that at that time, light was considered a wave, but those experiments led to the conclusion that light is also a particle. So we think of particles of light as being photons. And the third experiment from de Broglie and a whole bunch of other experimentalists led to the conclusion, kind of jumping off of that conclusion that a wave can be a particle, that particles can be waves, so that electrons also have wave nature. So these three experiments led to the development of quantum mechanics. So I want you to just read carefully this Chemist Toolkit 18. So on the very first page on electromagnetic radiation, you will have seen this in physics and for sure in Chem 107, but just reminding yourself of what electromagnetic radiation is. It's two planar waves of fields, essentially. One's an electric field, one's a magnetic field. This reminds you of those properties of waves. They have wavelengths, they have frequencies, and then the whole spectrum. So depending on the wavelength or the frequency, because they're related to each other, you might have radio waves, which are very low energy, or cosmic rays, gamma rays, X-rays, things that have a lot of energy. So read that toolkit, and I assume it's stuff you've seen before. But if you have questions, you can always ask. So the evidence for discrete particles, or discrete energies, comes from the experiments that you are very familiar with. So on this page, this top picture is for an atom. So you have very discrete energies, or wavelengths of light, that can be emitted or absorbed by an electron in an atom. So this isn't continuous. It's not just a flat, every wavelength could be absorbed, or in this case, this is emission spectroscopy. So somehow, if you remember in Gen Chem, you could use electricity to excite the electrons. And so this would be that process. And then when those electrons fall back to their ground state, they'd give that energy back off in discrete particles of light. This is the same thing, a spectrum for a molecule. It has many, many, many more peaks, almost becomes a continuum. But that's because a molecule can absorb energy in so many different places, vibration, rotation, the electrons, that you get something that looks different than this. You don't have quite as discrete, only because all those energies start to overlap so much. But each of these diagrams are showing you that energy is not a continuum when it interacts with atoms and molecules. The Bohr frequency condition allows you to think about what this means. So this means if a particle of light, a photon, has energy h nu, so that's Planck's constant times the frequency of the light, in order for it to interact with an electron in an atom, for example, the difference between the energy states, so the difference between whichever of these energy states you're going between, has to be equal to the photon's energy that's given off in that process. So if you go from E2 down to E1 in this picture, you're going to give off a photon of energy that's equal to E2 minus E1's energy. So that's something that you've used in almost, well, I bet in every single chemistry class. Every single spectroscopy is based on the Bohr frequency condition. So for that condition, grab this. So let's look at self-test 7A.1. It says we have neon lamps, and they give off red light with a wavelength of 736 nanometers. So if you look back here, that's in the visible region. So you'll be able to see that with your eye, red light. Some of the other frequencies you can't, like infrared and ultraviolet, but there is that visible region where your eye can interact with the light and you can detect it. So you have red light with a frequency of, or with a wavelength of 736 nanometers. We just want to know what's the energy of the separation for that emission. So we know something about the type of light, what's delta E. So the Bohr correspondence, or the Bohr frequency condition, says that the difference in the states is equal to h nu, Planck's constant, and this is frequency. In that little toolkit I had you read, it reminds you of the relationship between frequency, wavelength, and speed of light. So frequency is equal to speed of light over wavelength. So because I have the wavelength, I'm going to use this form of the equation. So Planck's constant is a teeny, teeny, teeny tiny number, 10 to the minus 34 when you're working in units of joules and seconds. So those are on the back cover of your textbook. The speed of light is a big number, 10 to the 8th meters per second. And when I take the wavelength of light in nanometers, given in the problem, and change it into meters, there are 10 to the 9th nanometers equals 1 meter. These units will all be consistent. So remember, a joule is a kilogram meter squared second squared. So it's the SI unit of energy. So if you have length in meters, mass in kilograms, time in seconds, you will have consistent units. So all of these will cancel, and your delta E will be in joules. So when I did that math, you get a tiny number because you're talking about 1 photon of light, so that should be a tiny number. So the next experiment that helped lead to the development of quantum mechanics is the photoelectric effect. So the evidence for radiation as being a particle. So at different times in history, light was understood in different ways, but about 1900, light was understood to be just a wave. So just to have the wave properties of electromagnetic radiation. But these experiments that were done on the photoelectric effect, you probably remember this from 107, but maybe not. So if you have a sheet of metal, and if you shine light on that metal, no electrons will be given off if you're below some threshold frequency. So if you're below that threshold frequency, you can shine as much light, as intense as you want, but no electrons will be ejected from the surface. And then you hit that threshold and electrons are emitted, and their kinetic energy increases as you increase the frequency. And even if you're at low intensities, you'll still get electrons. So once you're above that threshold, you get electrons. You get fewer of them at lower intensity, but the intensity doesn't matter. So this led to the conclusion that the electrons had to interact with packets of energy. They didn't just interact with the wave, they interacted with the particle. And so the photoelectric effect says that the kinetic energy, the kinetic energy that the electron leaves with is equal to the energy of the photon that's absorbed minus this thing that's called the work function, which is essentially the ionization energy. It's the energy that it takes to remove that electron from its interactions with the nuclei. So once you make that conclusion, all you know, so if you're assuming that light's a particle, then what you're saying is if the photon's energy is less than the work function, your electrons aren't going to be emitted. So that's what they were seeing. At some threshold frequency, electrons start to be emitted, but below that they aren't. The equation also predicts that the kinetic energy goes up as the energy of the photon goes up past that threshold, and that one electron interacts with one photon, and that energy goes into removing it from the surface and the kinetic energy of that electron. So we are going to look at self-test 7A.2. So we have ultraviolet radiation with a wavelength of 165 nanometers, strikes a metal surface. Electrons are ejected with a certain speed. Now they want us to calculate the speed if we used a photon with different energy. So sure, you could do this problem in different ways. What I did was use the first energy of the photon. So so calculated the energy of the photon. That's this first part. So Planck's constant times the speed of light times are divided by the wavelength. So I'm using the hc over lambda form. Says that in the first experiment, the wavelength of light is 165 nanometers, so 165 times 10 to the minus 9 meters. So when I calculate this first term, that's the energy of the photon. And it tells us the kinetic energy, or does it tell us the velocities? It tells us the speed. So it told us that the electrons leave the surface when this is the wavelength, with a velocity of 1.24 times 10 to the 6 meters per second. So I use that velocity to calculate the kinetic energy. So kinetic energy is 1/2 mv squared. And from the difference of those two, I'm calculating the work function. So the energy of the photon is related to the kinetic energy by the difference with the work function. So I calculate the work function. So that's the amount of energy from any photon that's needed just to get the electron off the surface. And then I can come back and I can say, what's the velocity of the particle if we change the wavelength? So the wavelength now is 265 nanometers. And so same exact calculation, but now I'm taking hc over lambda minus the work function to get the kinetic energy. Once I have the kinetic energy, I know the mass of an electron is 9.109 times 10 to the minus 31 kilograms. And I plug that in to get a velocity of 7.34 times 10 to the 5th meters per second. So the evidence that particles act like waves. The primary way that you determine if something has wave properties is by looking at whether or not it has interference. So when we look at these waves right here, this is showing us that when two waves interact with each other, they can interact in such a way to constructively or destructively interfere. So in A, the peaks and valleys are lined up so that the peaks and valleys get bigger, so that's constructive interference. On the bottom one, they're not aligned, and so high peaks and low valleys in the same place destructively or make that peak smaller. So it's that interference pattern that allows you to say a particle has wave properties. So you can do similar experiments to what they were doing with the photoelectric effect, but now rather than looking for particle nature, we're looking for wave nature of electrons. So you can pass electrons through small slits that are similar in size to them, and you can see that interference pattern. And so those experiments led to the conclusion that electrons also act like waves. And because it had just been concluded that waves, light, electromagnetic radiation, could act like particles, it was a logical conclusion. So in 1924, de Broglie came up with an equation that you will have used before that says the wavelength of a matter particle is equal to Planck's constant divided by momentum. And so we will do one more self-test, which is this one, 7A.3. No, you can read it. Calculate the wavelength of an electron that's in a 10 mega electron volt particle accelerator. So that's the energy of the particle. So, and it's all kinetic energy. So when we look at that self-test, we're going to use de Broglie's equation. And it starts right here. So de Broglie's equation, the wavelength is equal to h over mv. Mv is momentum. And so if I take the kinetic energy they gave me of 10 mega electron volts, that's equivalent to 10 times 10 to the 6th electron volts. And I can convert that into joules with the conversion that's on the cover of your textbook. So the kinetic energy in joules is right here. So I can set that equal to kinetic energy, so 1/2 mass of an electron from the table in your book, and solve for the velocity. Once I get the velocity, then I can just plug that into this equation. So the velocity I got is 1.88 times 10 to the 9th meters per second. Here's the mass of an electron. Here's Planck's constant. If you look at all of these units, let's just confirm that a joule, which is a kilogram meter squared per second squared, times a second, the units of Planck's constant, over kilograms times meters per second. That will cancel one of those. That will cancel that. One of those will cancel that. Then we have 1 over seconds, 1 over seconds. So those last 2 seconds will cancel. And we'll end up with a wavelength in meters. So that's the number that I got right there. So this joint, the very last sentence in this is important to think about as we go now into the need for a new theory and look at the development of quantum mechanics. There we go. This joint wave-particle character of matter and radiation is called wave-particle duality. It's the heart of modern physics and will be central to all that follows. So in our next little section, we'll talk about what these experiments told us and how that led to the emergence of quantum theory. So that's all for section A. So I'll see you in a minute for the next section.